Okay, so in the conclusion, say we have got this linear transformation from R2 to R2 defined by multiplying vectors by this matrix A. A has complex eigenvalues, and we have used the method of the previous video to write A equals P times C times P inverse, where C is one of these special matrices whose behavior we understand. Well, we have a theorem. It says that if we're in this situation and we choose to re-express our spaces in terms of a particular basis, then we're going to get a commutative diagram. And in particular, the bases we're using here well, the real part of the eigenvector, the imaginary part of the eigenvector. So the columns of P. And our theorem says that if we use the columns of P as this basis, then this transformation down here is multiplication by this central matrix. When we first saw this result, the assumption was that the central matrix was diagonal, but then we stated that we still have this result, whether this matrix here is diagonal or not. So what does that mean? It means that multiplying by any matrix with complex eigenvalues is essentially the same as multiplying by one of these special matrices. The only difference is what basis we're working in. So the three cases we saw when we were looking at these special matrices C, that we could have closed paths, or we could spiral out, or we could spiral in. Those three cases are also the cases we have for any matrix with complex eigenvalues. Now, this change of basis does distort things a little. So, for example, with this special matrix C, our options were R equals 1, r is greater than 1, or r is less than 1, where we recall that r is the length of an eigenvalue. These are still basically our cases, but we can see some variation. For example, we can see trajectories that look like this, that rotate around the origin in an elliptical pattern. We couldn't see that with these matrices C. With C, if you don't spiral out and you don't spiral in, your distance from the origin can never change at all. Well, this comes back to the fact that this matrix A acts like this matrix C, but it is not literally the same matrix. So you can see some variation here. What we're seeing here and what we see here are basically the same. They're closed curves around the origin. We just see some variation here due to the fact that, once again, the matrix A here is not literally C. And that gives us a little freedom. In general, however, we're either a closed curve, we spiral out, or we spiral in. Any matrix A with complex eigenvalues falls into one of these cases.